I think you're muted, Steph.
Our second speaker is Alice Jim. She's a fourth-year Ph.D. student in the Healthy Machine Learning Group at MIT, led by Professor Marzyeh Ghassemi. Her general interests are in deep learning representations and generative model for healthcare applications, and about integrating expert medical knowledge into machine learning models, ensuring medical validity and clinical relevance during evaluation. And here is her webpage as well. So, without further ado, I would like to give the floor to Alice Jean.
Oh, cool. Thanks, Steph, for that introduction. Let me see if I could get the presentation.
Yes.
Yes. Are you guys able to see?
We can see your screen. Yes.
Okay. Okay, cool. Yeah. So actually, I didn't expect Steph to introduce me so well. So yeah, I'm a fourth-year PhD student in Marzyeh Ghassemi's lab. And I kind of worked a lot in representation learning earlier, and I've kind of switched direction to diffusion models and medical LLMs. So if people are interested in collaborating in that area, I'm open as well. Yeah, so I'm presenting my earlier work during my master's for fair multimodal checklist for interpretable clinical time series prediction. So it's basically like we want to predict things like clinical diagnosis, and then we're doing these things with checklist models essentially. And the improvement and novelty here is how do we do this in a way that's both multimodal and also fair? So first, what are checklists when I say that? You could think of checklists as like these rule-based models that's based on learning what the Boolean threshold would be when you have a list of binary criteria. And it could be something like you will predict the positive class if m out of n items are basically satisfied. So a specific example here would be like you could predict contrastive car failure if more than 2 items are like checked off. And for things like continuous features, you will have some kind of threshold. So each individual checklist item is basically binarized. And the reason of like why would you want to use checklists is because it's actually used widely in practice in medicine already. And the reason for this, we really think is because first it's interpretable. You can actually see what the individual items are, and you could check it against your own medical knowledge and literature. And second, it's very easy to implement. So unlike models where even simpler ones are like logistic regression or XGBoost, you will need some kind of software to basically implement this in practice for these EHR medical record. Whereas in this case, like you just need a sheet of paper or you just have clinicians who actually know the criteria and they could very easily apply this to whoever kind of comes in. So how checklists kind of look in medical settings. It's, for example, we have 2 examples here. We have the Wiles criteria and the SOFA score for organ failure of sepsis patients. You see it's kind of similar to what we defined, where it could either be a score-based system where each individual binary item could have some kind of point system. And if you have like m out of n items, basically you are like low risk, moderate risk, or high risk. And for the SOFA score, it's even simpler. It's basically 3 kind of categories. And if you have 2 or more, basically, it's associated with a much higher increase in hospital mortality. And these are things that's actually very well established and have been well supported in medical literature and is used in practice as well. So we see here, like, unlike some of the more complex deep learning models that has more difficulty being implemented in practice, this is basically something that's already being widely used, and we basically want to kind of improve upon this. So some of these things we can't fully expect to be able to model with EHR data or radiology data, things that we're basically collecting into the system, because you see like so there's things that's based on physical observations. So things like the entire leg swollen or there's localized tenderness along specific systems. So these are things that's more physical. Which currently we don't have the ability to really put this into EHR data and actually learn from this. But we expect to maybe do it from notes. That's future work. So here we focus specifically on checklist items. That's kind of based on these observation-based metrics. So things like systolic blood pressure is less than a certain amount or more than a certain amount. And so the question here is like these checklists are traditionally kind of learned by these expert panels and by medical literature, and it's usually done by multiple studies that's actually been implemented in practice. But these studies we know could be specific to um, biases, essentially, basically what they were specific patient cohorts that they're looking at. So what we would kind of want to propose is more of a data-driven manner where you propose the problem learning checklist more as an optimization of an integer program. And in this case, as long as you have passive EHR data that's been collected, you could basically pre-process the EHR data and you could learn a specified checklist that we know works well and have been optimized for specific patient cohorts. And this allows kind of like customization and it takes a greater step in the step of like personalized medicine. Um, Specifically in medical practice, there's a sense of like both multimodality because oftentimes it's not a single modality of data that's actually being helpful, as well as like really strenuous evaluation of fairness and making sure that the models we learn is actually fair across subgroups. Specific experimental setting that we chose for our paper was the Mimic4 dataset. So this is inherently kind of a multimodal dataset where the Mimic4 is vitals time series data. It's a large DNFI dataset of like ICU patients that's been collected at Beth Israel Deaconess Medical Center here in Boston. And from this, we kind of summarize um, statistics of like the mean, max, mean, and standard deviation, sorry, as a typo, and range of these specific features. And then to binarize it, we basically bin them into specific bins. That's basically learned by this auto-binning program. And complementary to time series data, we look at imaging data. So these are the same patient cohort, but for some of them, we have radiology images and reports that's being associated during the stay. And then to binarize features, it's actually previous work that already done this. It's a chest image genome dataset where the features are already binarized into things like lung opacity, whether there's a pigtail catheter present in the radiology report or not. And a specific task we focus on is basically diagnosis of disease, phenotype classification, and we look at certain phenotypes within a patient cohort that has at least 10% prevalence for something that's actually a feasible task to do. So specifically what the multimodal data set would look like is like in red, we have a time series data set where you have heart rate and you have thresholds to basically binarize it. And imaging is basically a 0, 1 value already binary feature that's been extracted from chest X-rays. So how do we learn the predictive checklist? Well, you could think of reduction of the binary checklist as learning some kind of linear classifier. And this could basically be formalized into an integer program, which can then be optimized by mixed integer programming. This is work I've previously done in our lab. And then specifically, we use the IBM CPLEX optimizer to solve this problem. And in our specific experiment, we found that it was sufficient to really learn a checklist of like 10 items. And then we allow a maximum of 8 items checked off. And then we found kind of through different meta optimization that 24 hours is a good point to kind of stopping point for this. Afterwards, it kind of goes back and forth and it's for plateaus is what the metrics are. And we specifically optimize for balance accuracy here. What's novelty here is that instead of just doing evaluation for fairness, then making sure that it meets the subgroup fairness criteria, we explicitly can enforce fairness because we're proposing this integer program that has these constraints. So we looked at specifically the algorithmic fairness concept of separation during optimization. And you can interpret this as like, if you have a sensitive attribute such as like gender or ethnicity, you could have these gaps between attribute A and B, maybe it's like male and female, and you look at the gap between the false negative rate and the false positive rate, and you want this to be bounded within a certain interval. So in cases of perfect fairness, you would expect the epsilon to be 0, which is like, basically you want it to be exactly equal, but you know in practice it's not very possible. given data set. So this is actually a slack variable that we set specifically to 5% in our data set. So when we learned this, the first question we kind of want to look at was like, well, how useful is multimodal data that we look at here? So we'll look at the bounds accuracy and the F1 score across the time series only, the imaging only, and then the multimodal, which is like both of them are basically put in the pool and then learn to optimize. And you see here from the table that if you look at bounds accuracy, about like 8 out of 13 of them, the multimodal one is improving and better. There are specific cases where the image is better. And then we kind of looked at why could be the case. And for example, you have like heart conditions like conduction disorder and congestive heart failure. And we realized this was like basically very highly correlated with previous heart operations. So things like if you have a pacemaker, if you have these cardiac wires, and all these will basically always show up on the radiology. So it's almost sometimes like you're learning these proxy variables and bias from these radiology, then that's what basically showing up. It's making the imaging even better than if you do the multimodal, because it's kind of distracting when you add all these like time series features that it doesn't learn to optimize optimally. And then for pneumonia, it's a lung condition. So we expected that when we see a lung opacity, that's basically indicative of the condition. And there's specific cases where the time series is better, which is basically when the vitals time series is expected to be the most important feature. So things like blood pressure is very, very important for hypertension. It's basically diagnostic criteria. And things like fluid and electrolyte disorders is basically imbalance of things like sodium and magnesium. And basically all these are explicitly represented in our vitals time series data. So except for these cases where you expect very, very strong signal from one of the modalities, in other cases, generally it's better to kind of do a multimodal approach where you could learn signal basically equally from like both modality in these cases. And the second thing we want to do is like, well, we learned these checklists with a fairness constraint. Well, how did they actually learn this? So here we have a slack of 5%, which is shown by the dashed line across. And then here we're looking at necessity. And then in our data set, because we didn't have enough values of other necessity, we just basically grouped it into white, black, and other. And then the plot here, the red one shows the total gap. The blue dots show the false negative rate. And the green dots kind of show the false positive rate. And you see here, so at first, some of the dots are already below the line, see, so we don't really need to optimize them so much. But for all the ones where like you have a total gap above them, it really brings the gap between the false negative rate and false positive rate down. It's not optimal because it's hard to, in some cases, it's actually impossible to go to true convergence because inherent limitation to the data set, it's actually impossible to constrain it within 5%. But you see here that in all cases, like if you drop down, it's more fair. And we observe that condition for most of the cases. Conditions here, we repeat this experiment for basically sex, and then we see that, yes, we observe this as well. Most surprising to us is that actually a lot of the checklist that we learned previously without a fairness constraint is already pretty fair. So that's a little bit of a shocking thing. But I guess it's expected because we have a very large data set that's not known to have systemic biases. So we know that when looking at these metrics, it's more fair. But what does that actually change about checklists themselves? So we looked at a few examples of what the actual checklist output was without fairness constraint and with fairness constraint. And one thing that we noticed a lot was like, without fairness constraint, you see here you have a lot of different vital information here. So like oxygen saturation, mean blood pressure, temperature, and then you have like different imaging modalities that might be helpful. But with fairness constraint, it seems to almost like hyper focus on some of these vital time series data that we know to be correlated. But it's interesting how it hyper focuses on like heart rate, for example. And this makes sense for conduction disorder because it's basically a problem with the electric system that controls your heart rate and rhythm. So this would be directly reflected in the heart rate basically is abnormal essentially that shows up in the ICU rates. So you see here, like when you learn fairness constraint, It actually has the effect of like introducing less proxy variables, where it focuses very much specific on features that you know to be more specifically related to conduction. This is actually something that we want, basically, because it's something that matches more with clinicians because they look at these checklists with fairness constraint. They're like, oh, this makes make much more sense than something where like oxygen saturation and mean blood pressure might have some very complex nonlinear relationship that gets similar predictive results, but ultimately it's not going to be helpful for clinicians in practice because they're going to be hard to understand and interpret why these features are important in the first place. A second thing that we kind of notice is like if you have a modality that's inherently not useful, with this fairness constraint, it actually forces the checklist to learn less of the modality or depend less on the modality to learn a subset. So in the case of diabetes, uh, it's basically very difficult to learn from imaging data. We repeated this experiment multiple times, and then we realized that the data set itself is just like not informative for learning diabetes, essentially. Um, so in this case, when it's not predictive without fairness constraint, you have like kind of three imaging variables, and with that, you kind of like one, and then we kind of see this occurring a lot for these diabetes ones. And okay, so this kind of like concludes the kind of our exploration was like, oh, so with like imaging and time series data, this is how you kind of learn this in the multimodal setting, and this is how you deal with fairness constraint. We this was raised by someone who's a reviewer, and then we thought this would be interesting venue to explore, which is the idea of shapelets. Because how we pre-process the time series previously is kind of the summary statistic that kind of like basically bin aggregate signals into like larger time intervals of like 24 hours and then 2 hour intervals, and then you further bin them into like these thresholds to binarize. So, but inherently, these time series fine level data carries information on how it varies. So basic dynamics is actually important. So we were curious, like instead of imaging, what happened if we look at these time series dynamical data? So specifically shapelets, which is like very old classic type of work that look at the short segment of time series that could be used for identification, for classification. And then we run an experiment of time series only, which is vitals and vitals plus shapelets. And we see that most phenotypes doing to improve with the different shapelets. And if we compare this with the previous table of like whether adding imaging or shapelets better, it's kind of a mixed bag of like which one's more important. So in the cases where we learned previously the imaging modality is very informative, it's still imaging multimodal is better. In cases where vitals information specifically is very important, in the case that you will add shapelets to be improvement. Um, so specifically, let's look at an example. We look at congestive heart failure because oftentimes this is actually reflected in the fine detailed fluctuations of like respiratory, heart rate, and then blood pressure. So in this case, the previous five checklists are basically the vitals information, and then we kind of named them as shapelet one, two, three. They're not given specific names. So we could look at what it actually does. So specifically, there's ones that are positively correlated and other ones that are negatively correlated. So the ones that are positively correlated tends to be more fluctuations or changes or abnormalities. So shapeless one here for mean blood pressure is basically a very sharp decrease and an increase within 6 hours. So this plot here shows is the averaged. So we found where the shapelet occurs for all these time series of patient data, and we basically took the average across this window to identify what was the overall motif. And we see like within 6 hours, it's a very steep decrease and increase. Um, and because it occurs on a longer time interval, we see this repetitively. This is probably not due to artifacts, but is really due to a patient's experiencing a crash. That's basically very highly correlated with these congestive heart failure conditions. And the negative correlation is basically how stable the heart rate is for the past like one day, essentially. So when we see kind of like a plateau of these heart rates, it's been stable for 24 hours. This is kind of indicative of like the patient is kind of stable and less likely to basically experience congestive heart failure. So this is something interesting because shapes are they're kind of more satisfactory because you could look back at the data set and you're like, oh, so this is actually what's actually picking up on, essentially for these time stage dynamics. So that kind of concludes kind of our work and explorations. There are, of course, inherent limitations, as I first mentioned. So the checklist item that we look at basically restricted to recorded features, or basically any features that have been inputted into electronic health systems. We believe that it could be possible with this in future work to combine it with existing checklist systems, where for existing checklists that actually do have these threshold-based items, we could see for specific subgroups whether we could learn more customized thresholds. So essentially, it's a modification upon the existing checklist instead of learning something from scratch. The other possibility that I think is like more fun features, like maybe there are ways where the doctor records explicit checklist items into um, the joint clinical practice basically into the computer, and then the computer basically process these checklist items, even though they're physical observation based. So basically, you're using the doctor as a kind of first time data collecting, and then you put it into the system, which automatically runs a checklist. But what's good about this is that it opens up the possibility of the automated algorithm that's basically built on top of EHR systems, or the alternative is basically the classic system of like a checklist that your doctor basically checks off. One feedback that we also received from a clinician that we talked to was like, so the specific type of benchmark type that we focus on the mimic 4 benchmark task, oftentimes the clinician will actually know the diagnosis by the end of the ICU stay. So, and sometimes the task is like not so well formulated because you're not going to be in a very similar situation, basically in practice. And I was thinking in the future we want to look into tasks where it's how we expect the checklist data to be used in practice, essentially. So in very long chronicle data set, maybe you have very messy EHR data, but you could pre-process it into binary features that we predict things on a longer time scale, similar to kind of how checklists are used in practice. Yeah. And thank you for listening. That would be everything.
Thank you, Alice. Are there any questions? I don't see a question in the chat now, but you can post your question there. There is one question about Jovel is wondering if the fairness increased because the false positive rate and the false negative rate was reduced for the underserved group, or because it increased for the overperforming group. Would it make sense to learn checklists separately for males and females?
Yeah, so in this case, okay, so I guess the first question is very true. So we do see a overall slight decrease in predictive performance. So it's a kind of a trade-off between how the tight this lack of fairness is with how it impacts. So I guess overall speaking, it would be the overperforming group slightly being decreased. But we do see cases where you also have the underserved group being a increased performance because as we show in the checklist, it's being more focused on these like hyper-specific features that's actually very highly predictive. So it's kind of a mixed result that we have there. And I see that in practice, you will have to fine tune what the slack variable is for fairness. That's what we think is the most important part for implementing these. Because if you do this as too restrictive, it will be a big impact on basically the predictive performance here. And then for the second question, would it make sense to learn checklists separately from males and females? Yes, that's a different approach. So I think for larger sensitive variables, there is a way that you could kind of like learn these checklists separately, and then maybe that actually would be easier for medical validation because I think before implementation of any of these checklists, you need to kind of validate it by the medical literature. And then maybe in that case, you can actually look at systematic differences between the two. So this kind of depends on kind of medical accepted practices. So there's a lot of different debate about whether explicit guidelines should be different from these scientific attributes. There's people who say that it should be because these are clearly sometimes biologically driven, so you should have separate set of guidelines. There are people saying like these would lead just to more bias because you're giving different guidelines to different people. And then you're basically forcing whoever patient comes in to be categorized automatically into the separations, which actually is kind of dependent on how a clinician approach it, which actually could lead to bias. So yeah, I think it's an interesting question to think about whether we want to learn separate ones for different subgroups. But I expect that experimentally, if you learn it for separate subgroups, overall predictive performance will be better. So maybe the solution is to learn for each positive subgroup a specific checklist. One other issue that we kind of thought about was like the idea of multi-attribute fairness. So it's easy to think about you learn a fairness checklist for like, a female patient or a white patient, but how do you learn it for a white female patient, right? Once you really try to cross over all these sensitive attributes, in a lot of cases, we actually don't have enough data to actually learn a very highly specific checklist. Yeah.
Thank you. So, are there any questions left?
Yeah, maybe I can. I was wondering about those checklists. If it's always only like checking m out of n items, or if sometimes you can have like other scenarios. For example, certain like items in the checklist are more important than other, or if you like checked 2 out of I don't know 5, but those 2 correlated with the disease, it's enough. Or no, I don't know if you can comment on that.
Yeah. So how the integer program is written right now, so far we can't because once you have prioritization, it's no longer a binary system. So it'll be something more of like a ranking based checklist. And it's actually very difficult to fully write the integer program and solve explicitly. There's obviously like machine learning itself could approximate it, but for how we construct it explicitly with fairness constraint and an integer program, it'll have to be something where it's like a binary case. So anything that could be binarized could be constrained explicitly. So there's kind of trade-offs here where like, yes, you can have more flexibility with more complex models, or you can even go step above because in some sense, the linear regression model, logistical regression model could be interpreted as a fancier version of this. So with these ones, you have like the added value of like very explicit constraints that you could learn and be explicitly optimized for. But yeah, you are restricted basically binary cases in this case. Yeah.
Thanks.
Oh, thank you for your very interesting talk. I would like to hand it back to Amelie.
I think it's me now.